Howdy, welcome to my talk about GPU programming with Nim. Today, I'll introduce you to Hippo, a library I've been developing to simplify working with a GPU. My name is Andrew Brower. I am also known on GitHub as Monofuel. I use Nim professionally at work, but GPU programming is something I have explored as a hobby project. In case you are wondering about my GitHub picture, yes, it is a picture of me from when I was a Viking in Iceland. They did not have glasses back then. I just wanted to clarify that it actually is me because I once had a manager get very mad about it. Earlier this year, I read the book Cuda by Example. While it is a bit old, it is still a fantastic way to introduce yourself to working with GPUs. While working through the examples in the book, I realized that it should be possible to do the same thing from Nim, with little to no performance overhead. This led me to create Hippo, a library to allow you to write GPU kernels in Nim. Writing code for a CPU is very easy. Any programmer can throw out some Python or JavaScript to do a single thread of sequential work. For many tasks, this is enough to get our work done without much effort. However, most personal devices today will include a GPU. Sometimes these GPUs are small and integrated directly into the CPU itself. And sometimes we pay lots and lots of dollars for the latest and greatest shiny graphics card. These devices may have several gigabytes of super fast video memory, along with thousands of cores. It is mind-blowing to think about just how much power is in there. Why do we want a GPU in our system? How do we program them? Why are they so different? GPUs are designed for parallel processing, while CPUs are optimized for running a few complex threads. GPUs excel at running many simple tasks simultaneously. The key concept behind GPU programming is parallelism. Rather than processing data sequentially, we break the work down into smaller chunks that can each be ran simultaneously. This allows GPUs to achieve incredible speedups for certain types of tasks such as rendering, simulations, or AI. The first rule of programming a GPU is that your code must benefit from the speedup from parallelism. If speed or efficiency is not a priority, you might as well write a simple CPU solution that can take its time. This is why GPU programming typically involves languages like C++. Interpreted languages like Python or JavaScript are simply not suitable for this kind of high-performance work. For many real-world applications, you might not need to write your own GPU code from scratch. Instead, you can use existing libraries that provide GPU acceleration. However, if you do want to deep dive into writing GPU kernel code from Nim, then Hippo is the library for you. GPUs can be hard to program for. You can't just run GCC and compile Hello World to run on a GPU. To address this, NVIDIA invested early in building Cuda as a platform to make it easy for C++ developers to program them. Cuda C is sort of like an extension of C++. It adds annotations to specify which parts of the code should run on the CPU, the host side, and which to run on the GPU, the device side. Cuda lets developers control the number of threads that will run on the GPU. It includes functions for memory allocation, data transfer, and synchronization. The Cuda compiler, NVCC, handles compiling the entire program for you. It handles building both the GPU and CPU code. Then it handles linking in the runtime libraries to give you a simple executable that can use the GPU. It's really nice that they make all of this easy. Nim supports compiling to C++. Well, HIP is regular C++, and Cuda is basically also C++. But I don't like programming in C++, so let's do this with Nim. Hippo supports multiple ways of running your Nim code. It supports both Cuda and HIP, so you can work with NVIDIA or AMD. It also supports running HIP on the CPU, which is extremely handy for debugging, or also for running your code on a platform that does not have a supported GPU. Hippo requires that you have the Cuda toolkit to compile for NVIDIA, or the HIP compiler to compile for AMD. However, if you only want to target the CPU, you can use the define flag to compile as normal with Nim using your favorite C++ compiler. The library attempts to auto-detect the device based on your system, or you can also manually specify the runtime. Hippo does not automatically change anything in your NIM program. You need to do some work to specify what functions run on the GPU and how to move memory back and forth. Here is the simplest GPU program in NIM to add two numbers together. We define a GPU kernel named addKernel. This procedure is annotated as a Hippo global. Global means that this procedure will be ran on the GPU, but it will be called from the CPU. I can't read your mind and you can't read mine. Similarly, the CPU and GPU can't read each other's memory. So in this example, we have to manually allocate memory on the GPU for our output value. After executing the kernel, we can copy over the memory for the output variable and then display an output for the user. This is a very simple program that will execute one GPU thread, but GPUs are really meant for graphical programming. My next demo will be to show you how to generate a fractal using Hippo. Here is what a beautiful Julia set fractal looks like. Essentially, Julia sets are a simple type of fractal generated from a mathematical function, and they result in very pretty output. Let's break down the GPU code used to accomplish this. We start by defining a complex number structure to use on the GPU. This struct has both a real and imaginary component. For this struct, we define some functions to let us add and multiply complex numbers, along with a function to calculate the magnitude. These are all annotated as device functions, meaning that they will be executed on the GPU, but also called from the GPU. For the Julia set calculation, the Julia function computes whether a point x and y is in the Julia set. It uses an iterative formula to determine if the point diverges. If the magnitude exceeds the threshold, it returns 0 to indicate divergence. Otherwise, it returns 1 to indicate that the point is in the set. This is also a device function that will be executed once for every pixel on the image. The Julia kernel function is a GPU kernel that calculates the Julia set for every point in a grid. Every GPU thread will have its own x and y block index. This x and y position is the exact pixel that the kernel is responsible for calculating the Julia set for. The kernel function writes RGBA values to a buffer that represents the image. Each pixel is either red if it diverges, or black if it does not. This buffer is a visual representation of the Julia set. When we execute the program, we generate a GPU memory buffer for the bitmap image. Then we call the kernel to generate the Julia set and copy the memory back to the host. The code for both of these examples can be found in the Hippo GitHub repo. Hippo is still a work in progress, but it already supports advanced GPU features like shared memory, constant memory, and atomic operations. I would like to give a huge thank you to everyone who has contributed to NIM over the years. Libraries like Hippo are only possible because of the hard work people have done to make NIM flexible with powerful meta-programming tools. Thank you all for joining me today and listening to my journey into GPU programming with NIM. I hope Hippo inspires you to explore GPU programming further.